Okay, right. So, good afternoon, everyone. Welcome to the Area Zero webinar titled The Farming Future, Opportunities and Challenges in the Agricultural Energy Transition. As we have our audience joining, I'll say a few words before we start our presentation. So this webinar is part of the European Sustainable Energy Week. So here I would like to acknowledge their support for having us as an external event. As we all know, and many of us are already in this field for some time, agriculture is a critical role in society because it provides us with our food. And just this week, there has been a scientific report from the European Energy Agency that was sent out to the leaders of the EU that the bloc's coming agricultural policy needs reforms to incentivize more sustainable farming practices. So the good news is that we have solutions, and we have solutions that will not just be top-down policy, but innovations that farmers can adopt themselves, and that not only will reduce their environmental footprint, but will also have benefits for the farms themselves. So, yeah, embracing these innovative, sustainable technologies, some benefits for these farms could be simply to reduce costs, so lowering reliance on traditional energy sources that can have cost savings for the farms. They can make farms more self-sufficient, so farms can generate clean energy themselves, and they will be less vulnerable to, for instance, price fluctuations in the energy market. And also the environmental responsibility of the farms can be shown. So farms can demonstrate their commitment themselves to a greener future, and they can also have maybe new market opportunities by this. And hopefully these type of innovations could also lead to better product quality or reduced production, improved reduction as well. So today during the webinar, we are going to delve into the details of these type of technologies and this type of innovations. So let me briefly continue to today's agenda. We will hear from 3 ongoing EU-funded projects: Rest for Life, HyPErFarm, and TheGreefa. They will showcase their groundbreaking solutions for improving energy and resource efficiency in agriculture. Following these presentations, we'll have a panel of experts. They will engage in what hopefully will be inspiring and maybe even thought-provoking discussions on the social aspects and the acceptance of these new technologies. And then finally, we'll have 3 new members joining the Area Zero cluster: REGACE, PV for Plants, and Symbiosyst. These projects represent the continuation of this dedication within the field of sustainable agriculture. So, welcome to farmers, researchers, investors, policymakers, other stakeholders. I hope you'll enjoy today's presentations and the discussion as well. Your insights will be valuable, so I encourage you to listen, ask questions, and also engage in the activities throughout the event. And we'll have a bit more about how to engage later on. Before we start, I would like to say a few words on Area Zero itself. So it stands for Alliance for Renewable Energy in Agriculture and Zero Fossil Energy. This is an umbrella organization, and we oversee what we call clustering activities. So we bring together EU-funded projects, research and innovation projects in agriculture that are aimed at reducing emissions and reduce the use of fossil fuels. So we organize events such as today's webinar to build a community among the topic of net zero agriculture, to create visibility for the various projects, and we can learn from each other and share ideas. We were made previously made up of 6 partners, 3 already, 3 projects left: Agro Bioheat, Agro Fossil Free, and Renaissance. But after today, we hope to welcome the 3 projects that will be presenting the final session: PV for Plants, Symbiosyst, and REGACE into the cluster. But first, we will start with the 3 organizing projects: TheGreefa, HyPErFarm, and Rest for Life. Here we have our first session speakers today. I will introduce the first speaker. That is Serena Danesi, Research Associate at Zurich University of Applied Sciences and expert in solar thermal systems, thermal energy storage, and heat recovery. She is the project coordinator for TheGreefa, which means thermal chemical fluids in greenhouse farming. And this will be the topic of her presentation today. So without further ado, I would like to hand over the floor to Serena.
Okay, thank you, Jasper. I think you can hear me. So
yes, we can hear you.
Okay, so I suppose you see this presentation, so I can start. As you already heard, I'm the coordinator of the project, TheGreefa. The project started in 2020, at the end of the 2020, and in 3 months we are ready with the project. Sorry, I cannot. So I want to explain you very briefly what is the concept of the TheGreefa. So the TheGreefa is a new system, a new technology to control the air temperature, humidity in the greenhouse, and it's based on the use of salt solution that have a hygroscopic properties. What does it mean? That this salt solution, when it goes in contact with humidity air, can absorb the humidity of the air, so the air then is dry air. And during this process, is a condensation process, some heat is released. You can see you can see in this slide. But the innovation is that not in the property of salt solution, that they are very known. So in this way, we are able to store energy in the salt solution without losses. What does it mean? So the salt solution is very concentrated. Salt solution is liquid salt solution, but with some high concentration of the salt. For example, with magnesium chloride, we have more or less 40% for magnesium chloride in water. This salt solution goes in contact with humid air, typical from greenhouse, absorb the humidity, and heat is released. At a certain point, the salt solution is too rich with water and cannot absorb water anymore and shall be regenerated. The regeneration is the same process, but in the other direction. So dry air goes in contact with the salt solution with a small heat amount. So the dry air become very dry, the relative humidity goes down, and so the dry air can absorb the salt solution, from the salt solution the water, and so the salt solution is concentrated again and can start the loop again. What does it mean? So we need to regenerate the salt solution a certain amount of heat, and this heat is released then when the salt solution goes in contact with humidity air. This is a art to store this energy that's come from solar energy, so waste heat, in salt solution. So it's not, the energy is not stored as energy itself, but as concentration, and then it's released when we need. So these two processes are not at the same time. They can also happen at the same time, but they shall not be at the same time and at the same place. So we can recover heat in another place, store for more months, and then use in another place after 1 year and so on. So this is the innovation. The absorber where this process take place is very simple. You can see here some construction are actually plastic scrubber So the rotating component are just a ventilator for fans for air and a normal pump for salt solution, so are very easy. So the construction and the design can be different, but the concept what happen inside is the same. Why in greenhouse? So when we apply in greenhouse, you can see a small schema. What happens, especially in a continental region, the humidity normally is controlled by open and closing the window, and of course, by opening the window, we lose a lot of heat. With this system, when we I can go here, that maybe is so this is a standard greenhouse. So we open and close the window, we have some heat loss, but we can control the humidity. In the greenhouse, it's very important to open the window because the transpiration of the plant, otherwise the humidity become too high. With our system, we don't need anymore to open the window. That means we don't have these losses. So the humidity is absorbed in our absorber, and this absorber at the same time can release heat. Another advantage is that when we regenerate the salt solution, so the water from the absorber from the salt solution goes in the air, and with some other component we can also recover water from the salt solution. So we recover at the end the humidity of the air can use as water for irrigation and so on. This is the scheme with the photo of the greenhouse in Switzerland when we have our demonstrator. You can see here this absorber. We have at the moment 9 absorber. You can see here a scheme. So this is our absorber. Then the dry air is released below this table with the crop, and it's sucked from above. So this is our scheme. I don't have here the system. We install a similar system in North Africa, in Tunis. There we recover also the water from the salt solution, so the humidity of the air. But in Switzerland we don't need that, so we are not doing. Here you can see maybe the result of some tests in the Swiss greenhouse regarding the humidity and the temperature at the outlet of our absorber. Here above is the relative humidity in the greenhouse. In red, you see the humidity of at the humidity at the inlet of the absorber, and in blue you see the humidity at the outlet of the absorber. You can see that we can maintain the humidity of the right level of the setup. In gray here is when the absorber are not in operation, and you can see that the humidity increase very quickly. So with the absorber, we maintain the humidity at the right level, and the same for the temperature. You see here the temperature in red is the temperature of the greenhouse, and in blue you see the temperature at the outlet of at the outlet of the absorber. So we are able to maintain the temperature very constant at the outlet of the absorber. Here you have some peak, but this peak are due because in that moment we change the salt solution in the absorber, and the salt solution has a higher temperature. But you see, so the difference between the white area and the gray area, where we have the absorber in operation and where we don't have the absorber in operation. This is another scheme, another diagram where it's quite complicated to see, but it's the temperature in different point of the greenhouse. And the red is the reference temperature of the greenhouse. In this case, we don't have any more a constant temperature. The constant temperature is just at the outlet of the absorber. And in the different point, of course, we have different temperature. And now we are managed to try to have also a more constant temperature in different point of the greenhouses. With our system, we can also able to cool down the greenhouse, the temperature of the greenhouse, we have to combine our system with evaporating cooling. And you see here some graphic of temperature in June of last summer. In red is the temperature of the inside the greenhouse, not close to our absorber, and in blue you see the temperature above the table. So in any case, the temperature is more than 25 degrees, but it's acceptable for the greenhouse. You see that we decrease in any case the temperature at least of 10 degrees, and we don't need any electricity. So we need electricity just for some ventilator and some pumps, but not for chiller. So we save a lot of electricity doing that. And the temperature, I repeat, so if it was necessary to have a lower temperature, we were able to provide lower temperature with increasing the evaporating cooling. But for the operator of the greenhouse, from the greenhouse, this is a acceptable range. We tested this solution not just for greenhouse, but also for drier herbs and food. Of course, in the absorber, you can dry the air, and the air, then this dry air can use in a dryer chamber to dry the herbs. Then shall be regenerated with waste heat or solar heat. Here there is some result that I presented also in the last webinar about the energy balance in a dryer in comparison to a conventional dryer, and we can save more than 17% of electrical energy. This is a very good result, and so these are a previous result that inside of the project TheGreefa. Then we continue this project founded by the Swiss Federal Office for Energy, and we had really promising result. We also adapt the construction of the dryer. It's very compact and easy to install in a real situation. If you want to have more result, you can, here's the link. We have a report of this Swiss project. You can click there and have the report. I'm sorry, it's in German. But maybe you can translate, or you can know German, or you can translate with some tools. What is very also interesting is that for the generation of regeneration for our source solution, we use solar energy. This graphic is maybe confusing, very quickly explain. So we can regenerate our source solution also in the winter season. So at the beginning, we were quite surprised. So we were also supposing to regenerate a source solution during the summer when the temperature are higher, and in winter maybe not so. But we say that what is important in the case for the regeneration is not the temperature that we can reach, but the difference of the temperature of our soil solution and the air. So we need a temperature gap. We don't need the absolute temperature. So when the temperature of the air is 0 degree, is enough that our soil solution is maybe 10 degree and not 40 degree when that is the case when in summer we are 30 degrees. So the important is to have this gap. That means we can regenerate very well our soil solution also in winter when we have sunny days. So the limitation in winter is of course that there is less sunny day, and at least in our region, and that the hours of sun is less than in summer. But when we have sunny day, we can regenerate in the same way than in summer. I introduced before at the beginning and said that we have also another demonstrator, the greenhouse that we have in Tunis. The concept of a soil solution is more or less the same that we have in Switzerland. I repeat, we recover the water from the humidity of the air as water, and also we have this construction, so it's also possible to recover the water, so the condensate droplet on the surface, and this is then is used for irrigation. So this is some construction of our absorber, but if you have a question, I can explain better in answer. So this is the presentation regarding the TheGreefa, and I'm here for any question. Thank you.
Great, thank you very much. Yeah, so first of all, a message to the audience. So if you have a question, you can introduce your questions into the tool, but we'll try to either answer it right now, or otherwise, if we think the question is important, we can get at the end of the session, come back to it and ask it. So any questions from the audience, please feel free to put them in now. I will start out already with one question from my side then. Thank you very much for your presentation. My question would be, so how do farmers react to your solution? Do they kind of need convincing? Do they need to see a convincing business case? Or how do you convince them of the benefits for them of your solution?
So in our demonstrator, actually, we are not able to convince, because it was a partner of us, and he has electricity for free, actually. So you don't need to say in terms of cost. But it noticed that during the summer, especially during the summer, the climate inside the greenhouse was very good. And another point, not only regarding the energy, is very happy of our solution, because the plant, so the in greenhouse are actually there are flowers. The transpiration of the flower can be higher, because we remove constantly this humidity, and so here is also benefit in the growth of the flower. Here's some benefit in terms of energy. I repeat, energy just not in cost for him, but energy and for a growth of the flower. We have also another internal project in our university, because we are thinking that the contact of salt solution with the air can also have some benefit in the use of pesticide, because the salt is also dangerous for some virus and so on. So we are testing if we have the benefit in this sector. So less pesticide, because we kill the virus and the bacteria and so on, insect and so on. But at the moment in the greenhouse, we saw that there is some benefit in the growing of the plant, because they grow faster. And for this kind of flower, that means also more revenue for the operator. And now we want also to test the other one.
All right, thank you very much for your answer. At the moment, we do not have any questions there published, but I think we're also a little bit on time here. So what I suggest is any questions that come from the audience, we'll save it to the end of the session, and we'll now move on to the next speaker. But yeah, thank you very much, Serena. Yeah, thank you. Right, so our next speaker will be Wouter Merks. He has a background as a veterinarian, and since 2019 he's the director of TransFarm. He will explain this all to you in his talk, but TransFarm is an agricultural research site and business incubator as part of the KU Leuven, and this is also the project coordinator of the HyPErFarm project. So Wouter, I will hand over the floor to you.
Thank you. Okay, so now we can start. I hope everything is okay. I will talk about the HyPErFarm project, and the name is coming from hydrogen and photovoltaic electrification on farm. It's a Horizon 2020 funded project that started in 1920, and we are multiple partners coming from industry and research. So when I go to my next slide, I show you the objective of HyPErFarm. We want to demonstrate the effective decarbonization of farms by installing agri-photovoltaics while maintaining the crop yield. That's what we had as an objective and started up the research. And the aim is to provide and show a business case for farmers to facilitate implementation of renewable energy on farm, and to have not only electricity on farm, but to have hydrogen and a value chain for hydrogen on farm too. In the project, we had we have 8 different work packages. I will not go over them, but to tell you, and I go to the next slide because the pictures are nicer, but to tell you what is in the project, we had the aim of building agri-photovoltaics, so solar panels in between or above crops, to produce energy, being electricity or hydrogen, and to use then this energy on farm. This is the goal of HyPErFarm, to have demonstration cases with pilot setups that we build it on 4 different spots. And of course, the first part of doing so is having a permit and building the agri-photovoltaic sites. Here on the picture, you see that we have 4 demonstration sites, 2 in Denmark, on the right-hand side, 1 at Aarhus University in a vertical setup, 1 at a farmer's location, Hunsballe, with a tracker setup, with a side effect of having a windscreen or wind shelter for the crops behind it. Then we have a setup at Krinner Company in Germany. It's a horizontal PV system with trackers. And we had, or we have, an installation here at the University of Leuven at Transfarm. It's a horizontal fixed setup. The story to get there took us 2 years of the project because nobody had already experience, not at the pilot sites nor at the authorities, to install agri-photovoltaic systems. It was in 2020 very new, and I think what happened in between then and now is that agri-photovoltaics became more known. Everybody, or a lot of people, already know that it exists and that we want to do and crop production and energy production on site. So you see here in the pictures the 4 different setups that were finished during 2022, and where we have had 1 or 2 breeding seasons for crops since the start of the project, and the 3rd one is starting now in spring. So the second achievement after building these systems and calculating what was the need for the systems to build them was having crop cultivation in between or underneath. And here on the picture you see that we had our first breeding seasons. So at the left hand side you see the harvest here in Leuven of winter wheat in the first year. And I think you see on the second picture that it was a spinach cultivation during autumn of last year. Down the lower pictures are at the Krinner site in Germany, where was the seeding of coal and yeah, the big tractor or the big machinery activities underneath the solar panels. And then at the top right, you see a photo from a drone of the site in Denmark, where we have 2 different types of agri-photovoltaic setups in between crops. And you see the different crops, winter wheat again, alfalfa, and the 3rd one is, I think, the start of a grass clover that was set up there. And where we start with the cultivation. We had other crops in systems like pears, and in all these crop results that are not definitive yet, but that are preliminary results, we see that there is a reduction in what we harvest of about 20 to 30%. Of course, it's not only due to the system, it's also due to the season and due to the choice of crops that we made. But if it's potatoes, if it's a coal, if it's a wheat, or if it's a pear, we always see a reduction. Of course, at the other hand, there is a win in energy yield because there was none before, and now we have what the solar panels produce. Then our other achievements we had there, so we build it, we have crops under the panels, and then of course we want to go to a farmer application. And for a farmer, he does not want to build with a high investment cost before he knows what can be the return. So one of the achievements we made was to have a simulation tool that is online and for free, where you as a farmer or a farmer advisor can make a basic calculation on what can be the win in energy and what can be the effect on your crops when you install a system in your region on your farm. It's not only your region and farm, but also the size you want to include at your farm. And so this tool is online, only with few crop data for the moment, but we are working on it in the HyPErFarm project for this year, and we will continue to crop research under the panels for the next years to make the tool stronger. And then another application that was part of the HyPErFarm project is the use of biochar. Of course, biochar is not really linked with electrification when you look from a side, but here the aim is to produce biochar with solar energy, and then it can fit in the production plan. Here we do not have outside data yet. We see some crop data in greenhouse trials completed, but for the outside data we have to wait until the HyPErFarm project stops. And then, of course, I mentioned not only electricity, but also hydrogen and the hydrogen value chain. There it is quite new because our idea is not to buy in hydrogen and to use it on site, but our aim is to produce hydrogen ourselves. And therefore, on the left hand, you see a picture of a panel. These are standalone panels that produce hydrogen from themselves. We have now the first 3 or 4 panels outside mounted, and they produce hydrogen when the sun is shining well. And by end of spring this year, we will have a compressor unit finalized that compresses the produced hydrogen, cleans it and make it more dry, and we will use it as a part of a fuel for a hybrid tractor that drives on diesel and will use the hydrogen in its air inlet to reduce the diesel consumption and to remain its power. Again, the data will be there by the end of the project, but we foresee by the beginning of May that we can run our tractor. We did a desktop study on battery studies or storage systems on site, because we know that for a healthy business case on farm today here in Flanders and in most of the partnering countries, it is best to consume your own electricity and not to put it on the grid. That business case is not viable for the moment, but when you can be self-sufficient or partly self-sufficient, we made we tried to predict what type of farms benefit the best. And you have, for the animal farming, you have poultry winning the game. Swine production is the second one. For dairy, there is less profit in having battery storage systems. But of course, when you can produce your own electricity, it's always a win on farm level. And then the last thing I wanted to mention on this slide is that we do not only foresee in electrification of buildings and setup systems, but that we have some kind of robot, and there you see the robot of AgroIntelli that we are rebuilding in an electrified system again to have a user case on site for using the produced electricity. So these were the user cases. I think I talked about everything. No, I forgot to tell you that we climatize our animal units for poultry and pork with air heat pumps. And so we have a reduction of 100% of CO2 emissions today, and we climatize our animal units completely by electrification on site. So, but what is important too is, of course, that when it is interesting for farmers to start building, and what is the footprint of building systems. And when you go into the air with your solar panels and you don't use rooftops that are already available, you see on the right hand side that the cost of iron is really a heavy cost, not only in euros but also in footprint for your installation. So we are aware that not all arrows are green, but there are still red arrows even for sustainability looks. And there is, of course, a value proposition canvas that we made. And when you see here, we have more effect in production on our land because you have crops and you have electricity. There is also a new income from the energy because you don't have to buy it, or you can sell a little bit of it. We could not show yet that there are increasing crop yields, but there the crop research is ongoing. And of course, there are still high hurdles like having permits that is not easy, and then the link with the grid that is in farm areas quite far away, so a cost. At the bottom right hand side, you see then the network of possible stakeholders that can join us in electrifying and hydrogenizing farms, but I will go a little quicker. You see that we have looked not only to the economical side of the story, but also look to what are other people thinking about what we are doing. And therefore, our Danish partners created personas, and with these personas we started to do surveys on what is the perception of our neighbors on agrivoltaics. And the major lesson we learned is that we have to talk about what is agri-photovoltaics because people are not aware. So that's the first step before they can have an idea in yes or no, and we are working on that. And we involved, of course, a lot of farmers because they will be the end users of what we are doing in HyPErFarm. And as you see here on the pictures below, we have quite a lot of interest in farmers that are really curious in what can be a next option for them on their farm. And this was my light slide, Jasper, so I think I was quite in time, hope so. And I will stop sharing.
Great, thank you very much, Wouter, for your presentation. And we also have some interest of the audience already, so some questions came through here. So I will go straight for the HyPErFarm questions, leave the questions to Ms. Danesi to the end. So this one's for Wouter. For HyPErFarm, beside the project financing, were you able to obtain national financing help for installation of the PV?
Well, we had some internal funding of the university, and now during the run of the HyPErFarm project, we are more in collaboration with national parties. There is not really funding yet, but we are. Well, no, there is one project granted already, but there are some in the running. So you see that at national level, there is more interest now.
All right, great. Thank you very much. Next question here is the tractor part of the project or is it a commercial product?
Well, the tractor itself is a commercial tractor, but we are building together with one of our company partners a setup, a click-on system in the air inlet of our standard tractor that will allow us to inject the hydrogen. And well, we will do the first run in May of this year. But it's a commercial tractor where we will have an application, a click-on application, so it's not linked to one or more brands, the system that we do in the HyPErFarm project.
Thank you. And I'll do one more question from the audience before we move on. How did you decide the solar technology and configuration for each of the farms? Did you make a pre-feasibility analysis before to decide which technology to use?
Well, we have quite a lot of energy experts in our consortium, and the decision on building or on what we would build is made by the experts. It's not by us. And of course, of the availability of techniques that was there for at that moment. Do not forget, we started in 2020. It was a heavy year because of COVID and everything that came behind it. So to find companies that could build within the time frame that was suitable for HyPErFarm was part of the choice too.
That's very clear. Yes. All right. Thank you very
Okay.
much. If there's any questions from the audience, please feel free to put them in the tool. But we'll, in the meantime, move on. So thank you very much again, Wouter, for your talk. And we'll move on to the final speaker of this session, which is Alexander Loris. He has a background in mechanical engineering, is specialized in renewable energy systems. Currently works for MG Sustainable Engineering in Sweden, specifically on the topic of solar thermal and photovoltaic and thermal technology. He's involved in the design and installation of these very systems on the pilot farms within the RES4Live project. When you're ready, Alexander, then you can take over.
Yes, thank you, Jasper, for the wonderful introduction. And thank you to everyone, to the organizers for inviting me, and hello to the participants. So yes, as Jasper mentioned, I'm Alexander Loris from MG Sustainable Engineering. We are one of the 17 partners of the RES4Live project. And MG Sustainable Engineering was mainly focused on delivering the solar PVT systems for the three out of the 4 pilot farms of the project. Yeah, just a quick introduction on the RES4Live project. So we started back in 2020. We are a Horizon 2020 Innovation Action. We have 17 partners from 7 different EU countries. Here you can see all the different partners and where they're located. We're a 4-year project, and we aim to. Can you still hear me?
Yes, we can hear you.
Yes. Okay. So just a bit about the project in general. The goal is to. I don't know why sorry. To have market-integrated, cost-effective, and case-sensitive RES solutions towards fossil-free livestock farming. So there are different aspects to the project. A main aspect is to install and analyze and optimize innovative renewable energy technologies such as a PVT system, heat pumps. We actually have a tractor that has been converted to biogas, which is being used in a farm in Germany. And it's being used by the biogas that is produced directly at the farm. So that's technologies is one part of it. There are also other bits of research, for example, the thermal comfort of the livestock, of the pigs and the cows, that is being researched. And then other ways to have energy efficiencies within livestock farms, as well as smart control, smart energy control, energy management, and other energy optimization techniques. We have 4 pilot farms, and in 3 of them we have installed a solar system, and this is what I will talk about today. So just a a quick idea that I think is quite important. So thermal energy is half of the energy we consume on the planet is in the form of heat. And that being said, I'll explain a little bit about what a PVT panel is. Or rather PVT collector. It's a combination of a solar thermal collector, which is characterized by the tube that you can see. It's a pipe basically where a water glycol mix goes inside, the sun heats it up, and then out comes hot water. And then you have a PV cell or a PV module that's laid on top. There are different ways of making a PVT collector. In this instance, or the one you see here in the picture, is a well-insulated one, which is good for high thermal efficiencies. But then you also get some which are not insulated to provide cooling for the PV modules, because PV cells do not like heat. As they get hotter, they become less efficient. So PVT collectors are very interesting when you have low space availability and you want to maximize your energy production per square meter, and also cost per energy. So here you have a maximum efficiency collector. A PV cell can only be 20, 30 maximum percent efficient, whereas a thermal collector is 4 times more efficient at around 80%. So if you have a PVT collector, you'll have maybe 70% heat and 20% electricity coming out from one collector. So I'll just talk about, so in general, we have three pilot farms that we installed this technology on with 3 different PVT technologies, 3 different integrations with other renewable energy systems, and we have the same number of collectors per farm, just so we can compare between farms. So the first farm is in Ghent, in Belgium. It's the Ilvo swine farm. Here we have the PVT collectors providing heat to 2 heat pumps. One is a low temperature heat pump for floor heating, as the piglets need heat all year round, even in summer. And a high temperature heat pump for domestic hot water and some space heating during the winter. On the very right picture, you can see the collectors there. We have 24 collectors. So we have 24 collectors on each of the 3 farms. The ones here are insulated collectors, which have high thermal efficiency for maximum heat. The thermal collectors are connected to a short-term buffer tank, 800 liters of heat storage, and then the heat pumps draw the heat from the heat storage, and they create the heat for the actual farm. We estimate, of course, so these have all been installed during the course of last year, so we don't have exact data yet, but we think 24 PVT collectors will amount to about 25% of the heat demand of the farm. These are just some pictures of the electrical cabinet, which also handles the PV production of the PV modules, as well as the control of the thermal system, which is on the right side. This was an innovative solar pumping station that we created specifically for these projects, with the pump, the temperature sensors, the expansion vessel, and all the instrumentation needed to run the thermal system. Then we have Elvat Dairy Farm in Germany. Here we have a cattle farm, which has a milk chiller in the farm, and this milk chiller creates heat, which is being used by the farm. So we decided to take that heat and then further upgrade it. So the heat coming out will be around 40 degrees. It'll be upgraded to 50, 55 degrees by the PVT collectors. And then the remaining heat will come from an e-boiler that's on site. And that's being used for domestic hot water, cleaning of the barn, cleaning of the milk tanks, just general cleaning and usage of water. So here we have a very interesting type of PVT collector, which is a concentrating PVT collector. You can see the solar field on the roof in the bottom left. So it concentrates the sunlight to an absorber, which is under these PV cells that you see on the collector. The PV cells are bifacial, so that it's on the top and on the bottom, as well as having the thermal absorber at the bottom as well. So this solar field is then connected to a larger buffer tank. So there are 2 tanks of 750 liters each, making a total of 1,500 liters. And this is then connected in between the milk chillers and the e-boiler. So it takes in the heat from the milk chillers and then upgrades it to provide higher heat for the farm. Again, we predict that it can contribute to around 30% of the heating needs of the farm. Of course, just to mention, these are just pilot demonstrations. Of course, a farm can easily put many more thermal collectors to have maybe 90 or even 100% of their heating demand from solar thermal. Then we have our third pilot farm, that's the Goli swine farm in Italy. Here it's again a swine farm, and here we integrate again in a different way. So the PVTs are connected to a geothermal heat store this time. And it's a borehole geothermal heat store, which is also connected to a heat pump. So the boreholes will act as a seasonal storage. So the idea is to then store heat for the winter, which the heat pump can then use during the summer and in the winter, as they don't need space heating in the summer. Here, a different kind of PVT technology was used. This time it was uninsulated. So this was really, it's just a pipe with a PV module attached on top, much cheaper, more reliable, but also not as efficient. And since we don't need that much heat in this farm, we decided to go for this option, as it's also more efficient for the PV cells for electricity production. Because we've noticed that we predict about 90% of the space heating demand of the farm can be covered with this small solar field. But again, this has just been installed, so we're monitoring now the way it's working and all the data. So we want to get results on actually like how much they produce and how much it contributes to the farm. So just a last slide on some ideas. So what was difficult in this project was actually the fact, again, that it was innovative technologies. So there are no real regulations for this, and it was difficult to get installers to install the systems, as one, in general, plumbers and installers are not very familiar with solar thermal systems, and if they are, they often don't know the right way to install it properly. Sorry, this is the last point on the slide. I think this is also a very valid point for market uptake of the technology. Solar thermal needs to be more, let's say, regularized in the market, and installers need to know how to install them properly, as if it's not installed, it can cause problems in the future. There are very little subsidies for solar thermal and no subsidies for PVT systems, as it's a very new technology, but also quite a niche technology, quite rare. Yes, we had some trouble connecting the PV modules to the grid, as the authorities couldn't really place the product in their system, and the installers were not familiar with the technology or the innovative technology that we had, so a lot of them did not want to install it themselves or connect it to the grid. And then again, we realized it's quite a difficult task to make the different technologies work together. So the heat pumps with solar thermal, how do you effectively control them so that they work well together and they work in symbiosis? And the same goes with the geothermal storage. We are still working on the optimization of the control system and making sure that they're working well together. Just want to end with that. The solar thermal, including PVTs, is a very good solution, and it's generating some market traction. And we definitely saw that there is some a very good potential for livestock farming and agriculture in general, as they do need heat and electricity, and they do have the land on the roofs if needed, but they have sufficient space for this technology. So it is proving to be very, very good. Okay, that's it. Thank you.
Thank you very much. So I would say let me kick off with one question for you. So yeah, you say there's lots of different technologies for different situations, different farms or different kind of geographical locations. So it's really depending on the environment. So how do you think that you can help farmers or people who are interested to make the decision, kind of what would be the ideal solution for them?
That's a very good question. It all goes down on where they can buy it. So ideally, if you go to an experienced solar thermal retailer or installer, they of course would know what would be the best product or solution for them. But again, solar thermal is not very popular on the market. So the idea also of this project is to then get more popularity of the technologies and get it out there in the market.
So would your main argument to make it more popular be kind of the cost savings, or would it be kind of the fact that you have very high efficiency in terms of like per square meter, so like a lot of production for small spaces?
Yeah, well, for PVTs in general, it's a very good cost effectiveness, especially if you have low space. I mean, it's free energy from the sun. It's around 80% efficient. We generally see payback times around 5-6 years. And in general, it doesn't need much maintenance, just an annual checkup. But it's not a cost at all, actually. And they work very well. There's just not been a lot of people that know about it, and yeah, it's not really PV has dominated the market because of subsidies, and solar thermal has then kind of lost a bit of popularity, let's say.
Right, yeah. Okay.
But yeah, we are trying to, through these demo sites, we want to also invite farmers and get some activities going on around it, so to increase the awareness and to show that actually it doesn't cost that much, and it's quite it provides a lot of energy.
Okay, so before we go to the next session, like let's bring together the speakers one more time. So actually, I saw that Alexander, you also had a question for Wouter from HyPErFarm. Is that correct?
Yeah, I was just curious to hear if because I know I saw a picture where I saw the cells from the bottom, so I was wondering if you use bifacial PV panels also, or even transparent PV panels. I know that there are some transparent ones where you have like a transparent frame, but the cells are just there's like some transparency in between the cells.
Yeah, well, we use bifacials in the horizontal setup. In the vertical setup in Denmark, I'm not quite sure. It can be that we have two panels next to each other, but we use both systems.
Okay, thanks.
Right, and then there's also some questions here for Serena. So I will combine these two questions. So first of all, how does the cooling in the greenhouse work, and how much modification is required in the greenhouse to add your system?
Okay, so the cooling in the greenhouse is special because in greenhouse we have always to dehumidify. We have cooling in our process when we dry the air, but this is not the case of the greenhouse. That means in the greenhouse we dehumidify the air always, so we produce a little bit more heat every time. And for cooling, we have evaporating cooling. So combined to the absorber, we have also some spray nozzle of water. And this is the usual standard evaporating cooling that is already standard technology in the greenhouse. But if you humidify before, you have more cooling potential. That means if the air is already very humid, you cannot use evaporating cooling. If you dehumidify, so you move in another point of characteristics for the air, then you spray water and you have this cooling effect. And this is, I repeat, this is very good. Our greenhouse operator was very, very happy of this methodology. He has different greenhouses. In other, he has standard of evaporating cooling, but because he doesn't have the humidification, he cannot decrease the temperature so much with our system. So it's a combination of two technology, absorption and evaporating cooling. The other question regarding the modification required in the greenhouse, I will say you don't need modification, but you need additional component. So I share again my screen here. So you see the greenhouse. What we add in the greenhouse are these components here. This is the absorber. And of course, you need some pipe. Are pipe from the soil solution that in our case are around the wall. And the big desorber, so for the regeneration soil solution, is outside of greenhouse, is component like this, bigger with a diameter of quite 2 meter and is outside the absorber. That means you don't have modification. So we the existing heating system in any case installed and support our absorber when we are not able to reach the required temperature. So the increase of the temperature depend of the humidity of the air. If we are able to absorb a great amount of humidity, we can also produce more heat. If the humidity is not so high, the heat release also is less. That means in any case, you need a support, especially for heating, the classical heating system, and you need some space to install this absorber, but you have additional component. You don't need modification. I hope that it's clear.
Yeah, thank you very much. I think there's lots to ask still. We are limited on time today. We are already running a little bit over, so I'm going to end this session and thank you very much one more time for the speakers. So thank you, Serena, Wouter, and Alexander. So we will now continue with the panel discussion. So our great panel today will be moderated by Marleen Gijssen. She's from the Boerenbond. She will be the moderator. The other panelists are shown here: Raphael Herselin, Tom Schaken, and Petros Tegenal. They will introduce themselves in a moment. In this session, we will be asking you, the audience, for some input to fuel our discussion around social aspects and acceptance of the developed technologies. As an outcome, we hope to perhaps identify potential barriers and give recommendations to policymakers. So the panel discussion will start with an introduction of the moderator and the panel members. Then we will have a discussion around 3 propositions. The audience will be allowed about 1 minute to vote. So we ask you, the audience, to also raise questions and we can put them forward as we've done so far. We will start first with the first proposition for the audience. As we then await the results, we then ask moderator Marleen Gijssen from the Boerenbond to take over and briefly introduce herself, and also the other panel members can give an introduction as well. So I'm going to ask the audience to get your phone ready for the voting. and I will hand over to Marleen.
Thank you, Jasper. I think I will give the people a few seconds to enter the Slido, to scan the code, and to have a look at the questions and answer them. Okay, but I start with a short introduction of myself. So I am Marleen, I'm from Belgium. I'm from the Boerenbond, and Boerenbond is the largest farmers organization in Belgium, in the Dutch-speaking part of Belgium, the northern part of Belgium. I work as an energy advisor, expertise renewable energy, so is my colleague Tom. But since a few years, I'm also very active in AGIS projects, and AGIS stands for Agricultural Knowledge and Innovation System, where we try to get in contact, or to all be in the all share knowledge, produce knowledge, like the researchers, advisors, policymakers, farmers, of course, in the center of it. Okay, that's for me. We also have Petros Tegenau in this panel. Petros, may I ask you to introduce yourself shortly, please?
Yeah, okay. Good afternoon, everybody. This is Petros Tegenau. I work for ELVO as a scientific researcher. I am a mechanical engineer by profession, and I manage renewable energy installation for farms at ELVO, and also do thermal and fluid system modeling and simulation.
Okay, thank you. Tom, your turn, please.
Yeah, good afternoon to you all. I'm Tom Schaken. I work also for Boerenbond. I work at the Climate Smart Advisory Department, and I'm climate and energy consultant, and also active in the HyPErFarm project, aiming to develop call it a customer journey on agrivoltaics for the farmer, from an idea towards realization.
Okay, and finally we have Raphaël Bourguignon from Strain Innovation, I believe.
Yes, Raphaël Ercelin from Strain Innovation. So good afternoon, everyone. I work as a project manager in 2 European projects. The one was already introduced brilliantly by Serena. It's TheGreefa, and the other one is the proposal is on transparent wood. I have a background in agriculture with 15 years in the agro industry in South America. Thank you very much.
Okay, thank you. We can see on the screen, and I hope it's visible for everyone, the results of the first proposition. So the question was, 10 years from now, sustainable technologies such as heat pumps, solar cells, thermochemical temperature, humidity control will be widely integrated in farms throughout Europe. 1 is totally disagree, 5 totally agree. I see that no one totally disagrees. That's I think that's a good point. The majority of the people is convinced, but doesn't totally agree. Maybe some thoughts from the panel on this. Do you think, Petros, did you encounter challenges and obstacles when introducing your project to the farmers?
Yeah, specifically to speak of challenge, I don't know if I have to put it as a challenge, so to say, but like lack of information is, and also lack of training into technical schools about these technologies. So I myself have studied in Belgium. I have taken technical courses and also engineering courses.
Yes.
Yeah, the exposure, and also taught into Belgian university. These courses of thermomechanic machines and so on. So the orientation towards renewable energy technology valorization or introduction for the students is very limited, and you can see that also into the market. It was Alex was mentioning before, it was not easy to get a good installer for the PVT systems that we have. It was limited number of them, and also to get them in time, it was not easy. But
okay. So you
in 10 years,
Yeah, that installers have not so much experience with implying these technologies in agriculture.
Yeah, exactly.
Yeah,
And
okay.
yeah, maybe our training and education programs have to be a bit towards into renewable energies. Yeah, I think that the training orientation also have to be there. That's
Okay.
a bit of a challenge that we saw. And also economic consideration. Just we have run a short survey in farmers in Flanders. And yeah, the major constraint for them is lack of finance.
Lack of finance.
Yeah, lack of finance and or budget, so to say. And the second one was inefficient knowledge about the existing insufficient knowledge about existing technologies, and also insufficient knowledge about the need of energy or the demand profile in their specific farms, to speak it in technical terms. Yeah.
Yeah, Tom is a colleague of mine, so we know each other a bit better, so I can ask a bit more focused question, perhaps. Tom, we also see it in HyPErFarm or energy projects. I think we can relate to what has been said right now. In the specific case of the agrivoltaics, what do you think is the biggest challenge for implementing or integrating this widely all over Europe? What do you think are the biggest barriers?
First of all, it's like a colleague said, financing. What does it cost? It's a new and innovative technology, so the farmer wants to know what the real cost is and how to finance it, and for sure also how to exploit it. So it's also a question of what are the business models and how feasible are they once we have installed it. But first of all, you have to have the chance to build it. And I think specifically for agrivoltaics, we lack a definition of what agrivoltaics is, so that we have a common understanding of what an installation with solar panels above or between crops exactly is. Because we fail a facilitating framework and a legal framework that is comprehensive and clear for everybody, as well as for the policymaker understanding the installation and giving permits for it, as for everyone else talking about banks also want to know what it is and understand the complexity of an installation. So there are some lacks. So summary, good definition, and business models with which we can persuade banks and farmers to install them.
Raphael, do you also encounter some challenges?
Yes, of course, and I think they are almost the same as my colleagues here. First of all, I'm speaking about indoor farming. What is a thermochemical fluids? It's a bit frightening to the farmers. So first they need to get to know what it is, what is the technology. And then for specific indoor farming, the technical challenges include the adaptation of new systems to existing infrastructure, and the need for farmers and operators of training. So I think we have kind of the same problematic here. And also I would say that maybe we've run also a survey and assessment, a market assessment in 7 countries in Europe, and the conclusions were that there's a concern also financially, as it has been said, on the return on investment is one of the main concern of the farmers, because for greenhouses, almost everybody already has a microclimate system installed. So if they need to change, they need to know what would be the return, what would be the increase of the yield or not, the profitability of all that. So yes, those are the main challenges that we've encountered.
Thank you. We have been talking about farmers and installers. Maybe Jasper, can I ask you to go to the next proposition, because we haven't talked about the general public yet, and I think there are also some interesting things to say about social acceptance. So the question or the proposition is there is a lack of good information and educational programs for farmers and the public, and that's what I'm talking about, to raise awareness of how farms can play a role in the energy transition. Again, 1 totally disagree, 5 totally agree. And there is, yes, some time lap. Okay, people are filling in the survey.
Maybe we can already start kind of the discussion.
Yes, that's what I want to do. Yes.
Great.
Yeah.
Sorry.
I think this is indeed confirming what you have been saying during the discussion on the first proposition, of course, that there is a lack, and I think the public or our participants in this webinar also confirm this. Yes, there is a lack of good information and educational programs for farmers, but also for the public. Petros, do you have, because yes, solar boilers also are quite visible if you install them on a larger scale. Did you do any studies in the project on this social acceptance issue?
Yeah, that's pretty much what I have touched on to your previous question also, and yeah, how what we see from like the smaller scale surveys that we run through farmers in Flanders. Yeah, the lack of information about, for instance, the return of investment, the efficiency of the system that we are installing, and also a bit of a question onto the technology itself, like proven technology or tried technologies, what the farmers really want to see, like numbers on paper. What is seasonal performance of the system, for instance? This is the demanding questions that they bring about. So I still reiterate again the need of comprehensive education onto these technologies. I have been involved into one of the webinars from heat pump suppliers in Europe, and yeah, there was I know there is a good efforts that they are doing towards modularizing lessons into thermodynamics towards heat pumps also.
Okay,
that's a very good
indeed.
Work, and that should have to be promoted more.
Yeah, to increase knowledge and awareness. Okay.
Yes.
Yeah. Tom, agrivoltaics very visible, of course, in the fields. What is HyPErFarm doing, or maybe some action points or some findings in the HyPErFarm, or how do we try to tackle? That's maybe a better question. How do we try to tackle this issue?
Yeah, this issue is very important in getting permits, of course, because policymakers also listen to their voters, and these voters are the neighbors of the farmers. So we all need a common understanding of what is happening. But in the HyPErFarm project, maybe you saw it on one of the slides of Wouter. We have a topic working on social acceptance by using VR devices that project agrivoltaics installation into a landscape. And what we are doing is putting people to the test, looking into these VR devices, and we try to describe their reaction. So they will get questions as well as we look at their attitude, how they react. And by changing the images, we try to see if by looking longer and by changing angles and perspective, suddenly they start saying, oh, it doesn't look that big, or it doesn't reflect as much as I thought, and it's not that high as I thought. So in that sense, people get more understanding of what it is. And in the same exercise, we are working with personas, trying to get an understanding of how each person with a background of his own home, his own land, his own context, but also what he is doing, like, oh, it's a policymaker, it's a journalist, it's a researcher. We try to understand how they are looking at the topic and which would be the prioritized questions they will have on the topic. So that helps in understanding what are the real concerns, and so we can translate these in good research questions and requests on which we can try to have the right answers and arguments to tackle these concerns, and that works. So that's nice to have.
And bring them into policy recommendations. Yes. That will be the last question. But I first knowing some results of your project perhaps. Any thoughts on?
I'm sorry.
No problem. About social acceptance, but maybe that's a minor issue in your project. Maybe it's more about raising awareness with the farmers. That's what I understood from what you were saying beforehand. Yeah. Let's go to the next question, maybe. Let's go to the next question. Jasper, can you show us the last proposition? And we will also already start the discussion, or maybe like a synthesis of this discussion, because we are running a bit behind schedule. Yeah. The proposition is about more work that is needed by policymakers to remove barriers to promoting sustainable innovation and upscaling technologies in the agricultural sector. Maybe some last thoughts of each of you on recommendations for policymakers. And now I will start with Raphael, because I cut you for this last question.
No problem. Yeah, you're right. We're a bit late, so we need to be brief. Concerning policy making and how can we remove the barriers from promoting. Actually, in TheGreefa, we don't have such a problem. We're using a material which is magnesium chloride, which is a very common. It's used for de-icing also. So we don't have this kind of problem. But in a larger way, in a broader way, one can say that it would be great maybe to implement, let's say, a framework more adapted where policymakers they would be facilitating the adoption of sustainable innovation, and this would involve not only providing financial subsidies, but also simplifying, I guess, the regulatory frameworks. As I heard, for example, HyPErFarm, I think it's a bit more complicated in your case. So maybe simplified the bureaucracy would be the main target in my mind.
Yes, thank you. I think the farmers who are protesting right now in Europe will say that is absolutely true. Tom, any thoughts on this? Your last words on policy recommendations, please.
Yeah, the policymakers have these nice European goals, so they have to live to it and try to facilitate us. So regulatory frameworks and facilitating frameworks are really crucial. Yeah, we only can spend the euro once, and in that vision, policymakers most of the time concentrate on cities, industry zones and harbors, but that makes that our rural areas are most of the time a bit deprived of investments. And I think that our farmers have a pivotal role, because they have the potential to make more energy than they use at their farm. So they could be the most important partner in rural areas to accelerate the energy transition. But then we all have to work together with that farmer and give him this position. And then the idea of having energy communities working together, creating this common understanding of energy at a local level, will do the job. I think that's something we already experienced in a project, having a small energy community with 20 farmers and 40 people living together on 60 square kilometers. And it was hell of a job to start, but now they understand each other and suddenly it rolls. So every year they're doing a new investment on solar, on batteries, even in biodiversity and other topics like water. So now that they understand each other, they are also more often at the table, and being at the table makes things done, because then the ideas come to realization. So that's nice.
Collaboration pays off. That's absolutely
that's
true. Petros, you have the last words, and I saw you enthusiastically nodding with what the others were saying
Yes.
regarding these policy recommendations.
Yeah, definitely. I really agree with what the other panelists are saying about the topic. Just all the notes that I have are already mentioned. But one word I want to throw is transformational leadership that we need. Because these technologies, what we have at hand now, is going to change soon.
Yeah.
Like, because just everybody is researching about it, everybody's bothered about it, so solutions are coming up, and we really want the regulatory framework also to adapt as fast as how the technology is evolving. This is my word I want to throw. I agree with what
thank you very much. I think that's a big message. We are getting ready for the transition, and now people or the policy needs to follow. I really want to thank you all. I don't see any more questions in the chat or in the Q&A, and given the fact that it's already at 3:30, I think we can conclude this panel discussion. Thank you all.
Thank you, Marleen. Thank you, Raphael. Thank you, Tom, and thank you, Petros. We are going to go into the third session. Let's see. So our next speaker in the third session is David Moser. I think they're in the incorrect order here. So he's responsible for the research group Photovoltaic Energy Systems at the Institute for Renewable Energy, URAC, in Bolzano, Italy. He coordinates several EU projects and activities within the IEA Task 13, Performance and Reliability of PV Modules and Systems, and he's the Vice Chair of the European PV Technology and Innovation Platform. David, I will hand over to you.
Thank you very much for the introduction. I will share my screen, and please, if you can confirm that you see the presentation.
Yeah, I can see it.
Okay, then following your suggestion, I will try to be briefer than originally thought, but I will try to focus on the key messages of the project. So Symbiosyst is a project, Horizon Europe project, that started a little bit more than 1 year ago with 17 partners. And just as an introduction, I don't think there is a need to explain what is the potential of agri-PV in Europe or at national level. However, you can see a few numbers here that we also put in the ATPV Strategic Research and Innovation Agenda, just to show that we are talking about hundreds of gigawatts on agricultural land. I think it's important also to look at the possible impact of agri-PV at local level. So this is the case of Südtirol, so South Tyrol in the north of Italy, where I'm based, where at the moment it's not possible to have agri-PV systems. Here we have, let's say, an ambitious plan to reach the climatic targets, and we can see what the contribution of agri-PV could be on the left-hand side. If we cover 3% of the agricultural land for apple trees and vineyards, we would be able to reach the 2030 targets. Or the other option is to fill 24% of suitable rooftops. Of course, here the message is not that we should pick an extreme either entirely on agricultural land or on rooftop, but just to show that if we mix the two things, we could, agri-PV could really represent an important contribution to also speed up deployment, because it's not just about potential, it's also about installation rate. So what is the logic behind Symbiosyst? When we wrote Symbiosyst, we thought about the key knowledge of the partners, and a lot of the R&D and industrial partners in Symbiosyst come from a lot of experience in integrated PV, mainly BIPV. And we know that in BIPV, we made a lot of advances, but we made also a lot of mistakes, because initially we really underestimated the complexity of having several stakeholders like designer, architects, planners, city planners, policymakers who have different opinions about aesthetics and so on. And we thought that maybe we could learn from all those mistakes and make sure that we would not incur into the same mistakes in agri-PV. So here is just an example of how beautiful PV can be in various integrated in various infrastructure. And so those are the premises of the project of Symbiosyst. So we believe that the potential on rooftop systems is high, however, the rate of installation is low. We know that large utility scale PV is not a feasible option in many regions, especially in Europe. We have a lot of experience on the multiple levels of integration and the involvement of various stakeholders coming from the integrated PV sectors and what it means to have significant barriers for widespread adoption. And so we believe the agri-PV is in a unique position to learn from the past, to make sure that we don't get into the same mistakes. And also we want to make sure that we can avoid a risk, which is a concrete risk, to justify, to have a broad definition of agri-PV to justify large utility scale PV systems just by, let's say, cultivating some grass between the PV systems. So this is also something that could potentially represent, let's say, a stop for the whole sector, because it could not be accepted by the population. So what are the concepts and the ambitions? So we have several objectives from a technology, reliability, business, sustainability, and social point of view. We have several outputs that we want to develop in the projects. There is no time today to take you through all of them. I will present just a few. But I think what is important to say is that in Symbiosyst, we focus on both greenhouses and open agri-PV on horticultures, namely fruits and vegetables. And the concept for open agri that we have embraced is the concept that in Italian is called innovative elevated agri-PV. So agri-PV systems that can allow the cultivation of crops under the structures without, let's say, taking away any land, any room for agriculture. Those are the four archetypes that we have that are generally accepted as agri-PV systems all over Europe, certainly in Italy with the most recent norm. But the focus of Symbiosyst is on the elevated systems. And so the concept and the ambition is that we don't want to develop highly customized products. We believe that one of the reasons that BIPV is still not emerging as a let's say large market is that because there is a lot of customization, and if we do the same mistakes in agri-PV, then we could incur into a similar problem. So we will innovate by adapting on existing technology and existing processes. We will include aesthetically pleasing solution, but that can be mass manufactured and integrated. And we want to look into a two-way optimization in order to ultimately find a fully integrated solution that also gives the names to the project itself. So a mutually beneficial relationship between PV and agriculture. We worked a lot last year on a key message in terms of a policy paper that you can download from the website, where essentially what we state, the important message that we state, is that at the moment, agri-PV cannot be decoupled from innovation, that we need field experience, and we want to deliver a message that is not intended to create barriers toward extensive deployment of agri-PV, but rather to prevent an overly broad definition that could potentially include, let's say, open field installation that looks like agri-PV but should not be defined as agri-PV. So you will find all these messages in this policy paper that you can download from the website. So the methodology that we have devised is that we start from the assumption that we don't know everything. Actually, there is a lot of things that we don't know, and we need help from existing projects, like the projects that we were presented before. And we have included these demonstrators into what we call the demo drivers. Demo drivers are existing demonstrators that can share experience, data, processes, procedures, barriers that they managed to tackle, or barriers that are still there and can be shared with us. And then we hope in the future to be able to be in the same position and transfer the knowledge to what we call the demo followers. So we will have different demos in Symbiosyst. The main demos will be one on an apple orchards in Bolzano as an open agri, and on vegetables in Barcelona, also open agri, and then on a greenhouse in the Netherlands. So the example of learning is from, this is an agri-PV system, old style agri-PV system installed in 2008. I think it was probably the first agri-PV system in Europe, installed not far away from Bolzano. And we are going to install the new system close to that, also to show from an aesthetics point of view, how the sector has advanced. So the idea of the demo drivers is really the idea of provide valuable information on structure, data, sensors, monitoring systems, and so on. So if also I'm talking to the projects that were previously presented, if you have any experience to be shared, please join our demo drivers group. The way it's going to work is that we will organize events, calls together with the consortium of Symbiosyst, and we will see how we can mutually, let's say, benefit from this exchange of information. We want to innovate. We have a lot of partners involved in modeling, in looking into light sharing in open agri-PV, both on open agri and in greenhouses, and looking into the effect of albedo and reflectance. I will show you briefly some results later on. In terms of mounting structure for the open agri system, we are looking into single axis tracking systems with exploring different levels of semi-transparencies of the modules, and the integration of hail nets, of anti-freeze system, of irrigation and fertirrigation, and rainwater catchment. We are looking into robotic solution with the partners from Barcelona, for example. Here are some preliminary design, but in reality, the robot is already operating. It was demonstrated to us during the last meeting in Barcelona in January. And here is what it can do. So the robot can travel in the field, create a 3D mapping using LiDAR to create a digital twin of the crop of the agri-PV plant. It can do image recognition, and in this specific time of the project, they are going through training of images to recognize different types of leaves and the status of the leaves. Just a few details about the demonstrator in Bolzano. It will be a 90 kilowatt peak demonstrators with single axis trackers with the system at a height of 4.7 meters. We're going to explore different levels of semi-transparency, and we're going to look into the installation on an existing plant with the crops, but also we're going to install together with new crops, really to look into both challenges of introducing agri-PV system in existing and in new, with existing trees and with new trees. So to move towards the conclusion, so we are also looking into environmental and social justice through semi-structured interviews, and we're going to do it for Italy, Spain, Netherlands, and possibly Belgium. And it was interesting to see the paper that was published by the other projects. So far from Südtirol, we have more than 500 responses for the local farmers, and interesting to see that more than 40% would like to install an agri-PV system. We are looking into LCA and the development of KPIs, so to define what is a sustainable agri-PV plan from a social, environmental point of view. The scoring system will look like that for each demonstrator. And the future outlook is to have the demos ready by September, November, and in the coming months to publish about the social acceptance methodologies and results, about the LCA, the results of the LCA methodology, and the validation of the key performance indicators. And I would like to thank you for your attention.
Great, thank you very much, David. So I suggest to put any questions that are there from the audience to the end of this session, so we can gain a little bit of time. Yeah, we'll look forward to any questions from the audience that can be shared. And once again, thank you very much for the clear talk and interesting.
Thanks for having me
there. Yeah. So I would like to continue then now with the next speaker, which will be Esther Magadli. She's a researcher in the Al-Zahrawi Society TRDC Solar Energy Group. She has experience in building integrated renewable energy systems, both in industry and academia. Over the last 6 years, her research focus has been on greenhouse agrivoltaics, assessing the feasibility of using organic photovoltaics on Mediterranean-type polytunnel greenhouse roofs, and testing an innovative crop-responsive solar tracking system for inside greenhouses. Dr. Magadli is also co-inventor on the patent for this technology and co-founder of the startup company TriSolar. I would like to hand over to Dr. Esther Magadli then.
Thank you very much. I'm just going to share the screen. Can you see my screen?
Yes, I can see it.
Is it gone? Yeah, it's full screen now. Yeah,
full screen. Yeah,
great. So thank you very much for inviting us. I'm going to talk about the REGACE project. And yes, I'm talking a bit with two different hats. One is Al-Zahrawi Society, the coordinators of the project, and also TriSolar. I'm also, as you mentioned, co-founder of TriSolar, of the technology that is part of this research project as well. So REGACE is looking at a crop-responsive greenhouse agrivoltaic system in combination with CO2 enrichment in order to achieve both higher agricultural and electrical yields, and I will explain a little bit how that works. These are our partners in the consortium from various different countries, a combination of research institutes and commercial organizations, and also including 2 farms. One in Italy and one in Germany. So the whole idea, as I already mentioned, is to combine this greenhouse agrivoltaic technology, which is a tracking technology, a responsive tracking technology, in combination with CO2 enrichment to increase both agricultural and electric yields. So as I mentioned before, it's based on a crop responsive tracking system, which was developed previously by TriSolar, but is now in this project, we want to look at the combination of this together with the CO2 enrichment. The idea of this is that we can then have this technology appropriate for also lower light conditions, so in areas as well with lower light conditions, and testing them in different locations. So we'll be testing it in 6 different locations, which I will show in a minute on screens. But first I want to explain what the technology is about. So the technology is a crop responsive agrivoltaic technology for inside greenhouses. You can see here it's mounted inside the greenhouse. It uses the existing greenhouse structure to mount, so there are no additional structural elements, and is mounted above crop level, so it doesn't interfere with the agricultural work inside the greenhouse. The technology, so the tracking technology, as I mentioned, is crop responsive, so it can either do some tracking if there's too much light, and the opposite would be to be fully open when there isn't enough light, as you can see here. So it can provide full light by tracking the sun open, for example, or full shade by tracking it shut, and providing maximum energy output. So the idea here is to combine this technology with CO2 enrichment so that we can increase both electric and crop yields. The idea is that, so when you use CO2 enrichment with certain crops, you can work with lower light levels, and by doing this, our panels can face the sun more, so produce more electricity by doing this. And we're looking at this especially for more northern climates, so that this technology can also be appropriate for them. So there are different work packages. I won't go through all of them, but we're looking at different aspects. So the implementation, so adaptation to different greenhouse types. Then there's the testing of it. So looking at the effect both from various aspects, from both the electricity production to the crop yields, the crop behavior, and the greenhouse microclimate, and the effect of the CO2 enrichment with this as well. Then there's of course also looking at validation, also looking at the social aspects in this project, where our partners in University of Tor Vergata, they're looking at how this technology is sort of getting feedback from farmers, and they've done a bit of work which I will present in a bit of it as well on that side. There's of course also the economic and environmental aspect in the project. So the technology that I just showed will be installed in these different locations, and the most northern one in North Germany, and the most southern one in Kofokara in Israel here. And we have two farms that are shown in red, and then the other installations are in research centers / universities. And we're looking at different methods of CO2 enrichment. So we have the standard sort of CO2 cylinders that will be used, or CO2 cylinders or tanks, which will be tested in Berlin and in Volos. But in addition, we're also looking at using more sustainable ways of CO2 enrichment, using green offcuts or compost, or also mushroom cultivation, as shown in Vienna. Our partners on the farm in northern Germany, they already have experience with this from previously, where they put green offcuts, spread these in the greenhouse, and this naturally increases CO2 levels by about 200 ppm. So this is something we would like to test in combination with the tracking technology. So the idea is we're looking at it on two levels. There's looking at the way the technology works in these different climatic conditions, but also looking at how we bring in the CO2 enrichment part. So on the top picture, you can see that's our first installation, which has already been installed on the farm in Italy. And underneath you can see, which is the testing and measurements are just starting now, but at the same time already our partners in Berlin, they've been testing different light levels, different CO2 concentrations, etc., within these phyto boxes that you can see in the picture below. The idea is to combine these two aspects together to optimize CO2 concentrations where this is possible with the for example, CO2 cylinders, etc., and tanks, and also to see predict what effect this might have, and so we can optimize or adapt our tracking technology with the CO2 enrichment, which means we can change our values in the tracking software so that our light thresholds are altered in respect to the CO2 enrichment. In other words, we can play with lower light on crop level with the CO2 in the greenhouse in order to increase also electricity production. So these are experiments that have started. There are some more installations. So you can see the bottom right. This has just been completed last week in our greenhouse here in Kofokara, and we will be installing there's one installation currently taking place in Vienna in the university, and the others are on their way as well. You can see on the left the type of panels that we're using. These are custom-made bifacial panels, and they are semi-transparent by using the spaces in between the cells are transparent. So we have different configurations for the different sites depending on the conditions, so climatic conditions, and also depending on the typical crops grown there. So these are adapted as well according to location. So for the testing, these are the aspects that are looked at in the project. We're looking at the characterization of these different panels. That's the University of Rome's looking at that. There's the electrical monitoring in the greenhouses, which is Al-Zahrawi Society. The greenhouse microclimate measurements, which are, the task leaders are University of Thessaly in Greece, and crop monitoring is Boku University in Vienna, and water efficiency is Humboldt University in Berlin, and also CO2 enrichment is being investigated by them, and these expertises are sort of shared between the partners, so we're carrying out the same experiments or similar experiments in the different locations with the advice from the different partners and input. At the same time, there's a modeling aspect to the project as well. So the digital twins being created of these greenhouses, and different aspects are being modeled. So there's the greenhouse microclimate and energy, the CFD modeling, and modeling of the PV module performance, water efficiency, and the digital twins, as I mentioned. And this work's being carried out by the University of Rome, Tor Vergata, and University of Thessaly in Greece. So this is, you can see some pictures of the sociological environmental activities that have been carried out so far, the various aspects that are used. So there's the sentiment analysis, interviews, focus groups, and world cafes. And the first World Cafe has been carried out in Italy, where the first installation has been completed. You can see some pictures at the bottom there. So other areas that are looked at in the project is the economic sustainability, so looking at land impact from the PV systems, the resource efficiency, and also the circularity potential, especially also when it comes to the CO2 enrichment methods inside the greenhouses. There's, of course, there's the regulation aspect to it, looking at greenhouse agrivoltaic regulations and coming up with some advice at the end and feedback that is relevant to the technology in this project. And then there's the innovation management and business planning aspect, and of course dissemination and visibility as well that are carried out in the project. So I hope I've kept it relatively short, but thank you very much. And there's some, if you have any questions, even after this, if there's not a time for questions here, my email addresses, you can contact me.
Thank you very much, Esther. Yeah, no, that was great. That was a great talk, and you, yeah, we are running indeed a little bit over, but I think it was you kept it well within time. So without further ado, we're going to go straight to the last speaker of today, Dr. Selçuk Yersi, Associate Professor in the Electrical and Electronics Engineering and Micro Nanotechnology departments at the Middle East Technical University, lead researcher at the Center for Solar Energy Research and Applications, and his recent research is mainly focused on the development of high-efficiency solar cells and panels, including material growth, device simulation, and device fabrication aspects. A farmer up to the age of 18, Dr. Yersi is interested in solar panels development for agri-PV systems. Go ahead, please, Selçuk.
Yeah, thanks a lot, everyone, and thank you for the invitation, and those who are with us, thanks for staying. So I would like to introduce Pure4 Plant project. So it's an agri-PV system with climate, water, and light spectrum control for safe, healthier, and improved crop production. Thank you for a nice introduction as well. So we have 7 objectives. So ultimately what we would like to do is to boost the agricultural synergy of agrivoltaic technologies to enhance the growth conditions and increase the land use efficiency. So I'd like to do this by, as other project also aim the same. So we involve the end users in the design process. So we are actively getting feedbacks, and we will be getting after installation, and creating of highly replicable methodology to elucidate the crop performance. So I'd like to hopefully give one design that can work for many crops, and this is what we are hoping as the other 2 projects also. And but we have the spectrum management and transparency management in slightly different ways. So we both have the rotating panels and tilting, and also a little bit of photonics inside the panels, which I will explain. Adaptive modular initial Pure4 plant design and to specific pilot requirements. So we'll have 3 pilot positions. We'll have the first one after 1 year, we have the second one after we have the third one. So it's a gradual improvement, hopefully within the years as well. So we'll be using bifacial solar panels and with some color converters. Proactive facility control and operation for agri-PV system, increasing the PV output and plant growth conditions. As also mentioned in the previous talk, so we'd like to prioritize the plants when needed, or switch to the PV to improve the PV production when needed. So we would like to have something in a balance. Increase the share of the recyclability and reusability in all phases. Demonstrate and validate the solutions and different agri-PV system and configurations in wide range of scenarios and climate conditions. So we'd like to install 1 in Turkey, 1 in Spain, and another one in Denmark, so that we can have sort of at least 2 different geographical climatic conditions, 3 different geographical conditions. And boost the scalability and replicability via evaluating the financial support mechanisms in multi-criteria assessment, innovative local and rural business models. So as I said, we have 3 locations. The first one is this is going to be installed this year, Bursa, Turkey, and it's going to be tomato and green peas in summer and in winter. And then the second one will be in Avila, Spain. It will be for microalgae. And the third one is going to be in Denmark for grass, Spanish, and lettuce. So in our consortium, we have a spread of the partners and also spread of the knowledge that they are bringing into the project. So we'll start with the work package number 1, which we call, and it's user acceptability. So DTU is mainly taking the role with Glue. And we have already started doing surveys and got the first results, which I will show in the next slide. Now we have lab testing methods, so which is in Sheffield University, there are conditioned rooms. And in those conditioned rooms, we already start growing some tomatoes and then understand the spectrum, the effect of the spectrum on those tomatoes. Then we have the spectrum engineering part by Yıldız Technical University and us, Otuginam. And we fabricate the modules in Kalyon PV, who is the coordinator of the project and also a big PV manufacturer in Ankara. And we have smart farm sensing and R2M solutions for the irrigation and all the controls that we have. So irrigation, the position of the panels, and so on and so forth. And Avila is helping us in the cost benefit analysis with their large infrastructure. So Ambiente Italy is responsible for resource efficiency and LCA. Then we have the financial model by NR2 Crowd, and we have the implementing partners of Sierra Avila, TAT, and Tekes Garderi. So I also would like to show some results while presenting the innovation. So this is the first one, and the user acceptability part. We already start doing the surveys, and these are the first analysis that we have. So far, so good. Let's say the people are happy that AgroPV is going to be implemented in their fields. And these are not only the farmers, these are all the stakeholders that you can find near the farming region that we are going to install. And the second one is the main innovation. And the one on the left actually shows it. So what we have is we have an idea to control the red light emission by reducing the light from blue and green. And this red light control that we can do it both in the position and also intensity wise. So now what we are doing is we're trying to understand the effect of this additional red light on crops that we are going to use. And in Sheffield University, inside the closed rooms, in a very controlled environment, these are exactly the same crops, and the soil is mimicking basically the soil of the region that we are going to make the real implementation. And then we have this the control strategy that will prioritize to plant or the electricity production. And we also have this almost full coverage of the farmland when needed, so that we, for different climatic conditions, for the global warming, we can adapt our system to collect the water or to, for example, reduce the snow load or to protect from the heat waves. So to achieve those goals, what we started doing is we develop a simulation and test platform. So basically the light is coming, and then we trace every photon and see if it is going to be on the photovoltaic or on the plant. If it is on the plant, what color it will be. And then we compare this with our indoor experiments, and that's so that we circulate this idea to finalize what design it should end up at the end. And then the other one, as I said, we are already using the indoor facility to understand the effect of this red light. So how much should we increase or how much we should shift it, because we have a valve control in this position. And the first results we already received, and I'll just only show one interesting, well, one not very interesting one. It's the flower number among the three groups. And the number of flowers are pretty much the same, but we do see differences in some other parameters. And after this, as I said, the circulating between the indoor experiments, simulations, and the fabrication of the control systems, we end up different designs, and we had to choose one. So some of them are better for photovoltaic, some of them are better for the plants. Better means more generation, more light reaching to the plants, or more electricity we can produce. So we picked the third one because it is relatively easier to fabricate for the first year due to the time also stress that we have on us, because we need to finish this one in a few months from now. And this is the data that shows the spectral shift. You see we can reduce the peak intensity. This is the real sun you can think of. And we can reduce to 500 nanometer, which is the green light. And we can shift this spectrum to the red light right here. So which is kind of working fine, and we fabricate the 50 panels already. We need to reach about 250 because we would like to see the microclimate effect. So want to make it a bit large. And this is the design that is going to be ended up. So we have one field, which is what we call is our innovation part. And then we have the other one, which has the exactly the same shading ratio, but made out of standard panels. And then we have another reference field, which is just have nothing. It's just an agriculture itself. So luckily, we have also a national project where we can change the spacing between the solar cells and make it more denser compared to this one. So we just try to combine other projects onto the same field so that we can make more experiments, more controlled experiment in the field. This is hopefully how it is going to look like in about 2 months from now. That's the goal, because we would like to catch this tomato season. And this is how it's supposed to look like very soon. So this is about the Pure4 plant. I just have 2 slides, and this is the Turkey first agro PV project that is live now. We installed this about like 6 months ago. We already harvest 1 set of products, so it's the reference field, and this is the PV. So we hope to join David and share the experiences that we already have, and which is right now ongoing, and we are trying to make it smarter by, for example, automatizing the irrigation and so on and so forth. So the other one is a little bit of announcement. So the 3rd to 5th of July in Ankara, we have a PVCon conference. It's a conference that we have been organizing for quite a long time. Now I think this is the 6th series of it. We will have an agro-PV panel. As I have shown you, the Turkish industry is pretty much interested in agro-PV, and they're pressuring a lot on the agricultural ministry, and we would like to increase the agro-PV system in Turkey so that we can make more analysis before any law start acting on. So thank you for listening.
Thank you very much. Thank you, Dr. Yashi, for sharing this talk here. We run slightly over, but I think there's still room for maybe getting the last speakers together. And I thought of a question that is, because we've seen 3 talks that show kind of 3 use cases of agri-PV, but each with the kind of their own innovation there. So really interesting to see these different directions. So I was actually wondering what you would say, and because we have 3 different kind of approaches here, I think the answer would also be kind of different for each of you. So what would you say would be your main argument for agri-PV instead of just maybe installing a kind of an open field or rooftop solar panels, which may have kind of for farmers maybe easier to understand or have a much clearer like value proposition. So yeah, maybe you can start with Selçuk. What do you think in your case?
Well, in the case of agro-PV, not the system itself, or the agro-PV in general, I think we are a bit in a lucky location, if you can call it, because Mid Anatolia is already water stressed. So that is the agro-PV. I think the most benefit that we will be getting from these systems is the saving of the water, because now we are fully covering in the system, or at least design that we have, we are fully covering the field when needed. Although the glass itself has some openings on it, but then still, when you consider the evaporation of water from the plants, we just cover the top, right? So that supposedly should reduce the loss of the water. I think this is where we will benefit a lot in our systems. And in general, what we are hoping that also we have this water irrigation system that is coupled with the rainwater harvesting and the snow, which didn't happen this year in mid-Turkey, unfortunately. But hopefully we'll have snow load at some point. So this is number 1, I would say. And number 2, I'm quite optimistic that this the spectrum shifting may give an additional boost to some of the crops, but this is something that we should see in coming years.
Yeah. Okay. Very clear. How about Esther? What would your answer be to the question?
So I agree with your answer, Serkan, as well. But I think that I have sort of 3. I think there are 3 areas. One is obviously the climate change aspect, the different a lot of desertification happening around in different parts of the world, which make areas not suitable for agrivoltaics anymore, and this can really help by really protecting the areas and the plants and creating these other conditions, growth conditions for plants. So there's that aspect. There's of course the dual use of land aspect, which, you know, we need land for PV systems, and this is the well-known, you know, agrivoltaic solution in a way to use it twice. So that there's obviously that aspect. In order to increase renewable energy uptake, etc., we I think this is agrivoltaics is really crucial in that equation. So. But then, of course, also the advantage for farmers. So, you know, if farmers can create an additional income by producing energy as well, or by using the energy themselves, as was also shown in some of the other presentations before, that's another advantage. And I think possibly for a farmer, possibly one of the most important aspects. So, yeah, so those are my 3 points.
Yeah, really. Thank you. Yeah, thank you. David.
Yeah, not much to add. Of course, crop protection, water collection. So the integration of the system, they're allowed to do things that can be already done, but by using passive solution. Here we are combining active solution with passive solution. So if the aim is solely the aim of producing electricity, then I agree with you that it's difficult to sell the concept, but it's wrong, you know, it's the wrong assumption. So here we are selling an integration that gives way more than just electricity production. And then I think the differentiation between the 3 projects is that we look into solutions to cover a broader spectrum of agri-PV. So it's very nice. And I think that the discussion between the 3 of us will be on cost at the end to make sure that cost-wise they can have a market, but there are a lot of industry partners behind it. So I'm sure that the question of cost is in the heart of all 3 projects.
Yep. Right. I think, yeah, so once again, thank you very much for your contributions. And I think that this is not the end of the discussion here. As your projects are just starting, I think it would be great to have that conversation continuing, hopefully through also partially through the Area Zero cluster. So I think because we have already run over, I will close today's webinar. So thank you all very much for attending the webinar. I enjoyed hearing about the variety of these innovative approaches that were presented. I was surprised to learn that one of the main barriers to the technology is actually just explaining how it works to users, and maybe even to people who install the system. So, and as we learned also from Symbiosyst, that kind of the definition of really matters, like how do we define actually, how do we make sure that we are very precise in how we define the system. So that was really interesting to learn. The panel discussion was interesting. We learned about that end users may need some convincing about visibility of the business case, and that policymakers can really help by removing paperwork, providing much needed financial support, because yeah, as was said, farmers are crucial partners in the energy transition. So I would like to thank the EU for funding the incredible work seen today, the European Sustainable Energy Week for having us as an external event. And then I would like to thank all the speakers and panelists, Serena Denesi, Wouter Merks, Alexander Loris, Marleen Gijssen, Raphael Herselin, Tom Schaken, Petros Tegno, Selçuk Yersi, Esther Magadli, and David Moser. I'd also like to thank my incredible co-organizers who have been working hard also behind the scene today. Jakob Pluta, especially for making sure that today's webinar was running smoothly from a technical and IT point of view. And Anna Spoden, especially for her great work on the communication and promotion around the webinar. Thank everyone for attending the event. This recording will be made available on the Area Zero website and YouTube channel. Feel free to contact us in response to the topics discussed today. And yeah, hopefully we can keep that conversation going about technological innovation for the agricultural energy transition. Thank you very much. And with this, I would like to close the webinar.